Welcome to Lecture Online, and here's a new chapter on astronomy called The Nature of Stars. And what we're discussing in this chapter is the various aspects of stars. For example, how far are they away, how big are they, how bright are they, how luminous, how long do they last, how are they born, how did they die? Lots of questions about stars that we'd like to answer. When we go out there at night, for example, let's say you go to the mountains or the desert, and there's no city lights anywhere near, and you look up in the sky, you see just a myriad of stars. In actuality, you see about 3,000 of them. Now, if you could walk to the other side of the Earth on the same night, which I guess you would jump in an airplane and fly the other side and look at the stars over there, you would see about another 3,000. In totality, we can see about 6,000 stars with the naked eye. Of course, from any one location on the Earth, that's only about 3,000, half of those. If you grab a pair of binoculars, you can see anywhere from 10 to 15,000 stars, depending upon, how good your binoculars are. Maybe a really good pair of binoculars, you could see as many as 50,000 stars. And then when you grab yourself a 6-inch telescope, you can see about 2 million stars. It's quite amazing. When you take a look at them very carefully, because normally people think stars are all alike, some are dim, some are bright, but actually if you look at them closely, they do have different colors. Some stars have a bluish color to them. Some stars look more white. Stars like our sun, they're yellow stars. We also have orange and red stars. And so you wonder, well, why do stars have different colors? Why do they have different brightnesses? In some cases, stars even change their brightness in a matter of days. So there's a lot to be learned about stars, and this chapter is going to address some of the basic concepts, the basic nature of stars. So if you're interested in this chapter, stay tuned. We have a whole bunch of videos that will illuminate the information and our knowledge about stars. Welcome to Lecture Online, and in the second video we're going to take a look at something called the apparent magnitude. It's a means of determining which star is brighter and which star is dimmer. And again, the key word here is apparent. Apparent, the way it appears to us. Because it could be that there's a really bright star that's really far away and looks really faint to us. And there could be a very small star that's really close and appears very bright to us. So it doesn't tell us anything about the actual brightness of the star or the actual luminosity, but the apparent brightness. And so in astronomy, we have a scale that indicates which star is brighter and which star is dimmer. And it's called the apparent magnitude scale. And it turns out that on this scale, the smaller the number, the brighter the star appears. And the bigger the number, the dimmer the star appears to us. So it's kind of counterintuitive, but that's how we do it in astronomy. And it turns out that the brightest star in the sky, Sirius, has a magnitude of minus 1.4. And yes, a negative number means brighter than a positive number. So here, for example, let's say we have 3 stars, star A, star B, and star C. And let's say that star A has a magnitude of minus 1, star B has an apparent magnitude of 4, and star C has an apparent magnitude of 9. And I should say apparent magnitude because it's how it appears to us. We have another magnitude scale, which is called the absolute magnitude scale, which indicates how bright the star actually is. So here we're talking about the apparent brightness, how bright it appears to us. So of these 3 stars, which one is the brightest? And by now you should realize it's the one that has apparent magnitude of minus 1, and star C would then be the dimmest because it has the largest number. And star B would be then somewhere in between the two. Now, if you want to ask yourself the question, how much brighter is star A compared to star B, and how much brighter star B compared to star C? Well, we'll explain that in just a moment. One more thing I should mention, that not absolute, but apparent magnitude of +6 is the faintest stars that we can see with the naked eye. So any object, even galaxies or nebulas that have a magnitude, or star clusters, for example, that have a magnitude of +6, those are barely visible with the naked eye. And if something has an apparent magnitude of +7, it's no longer visible with the naked eye. We actually would need a pair of binoculars or a small telescope to be able to see those objects right here. So how do we compare the brightness of one to another? How do we convert that to something that we're more familiar with? If, for example, if I wanted to know how much brighter star A is compared to star B, how do we figure that out? The way we do that is we count the difference between the two magnitudes. So here the difference between -1 and 4, call that delta M, and sure enough the small m is what we use to indicate apparent magnitude scale. So we use a small m for that, we use a capital M for absolute magnitude scale, and we'll see that in another video. So we look for the difference in the magnitudes, and in this case the difference between -1 and 4 would be 4 minus and minus 1, which is 4 plus 1, which is 5. So you can see that with a little arithmetic we find the difference in the magnitudes. And then to find out the difference in brightness, what we do is we take the number 2.512 and raise it to the difference in magnitude. So in this case, that would be 2.512 raised to the fifth power, because that's the difference in magnitudes, and this is actually equal to 100. So here you can see that star A is brighter than star B, and someone asks how much brighter? Since the difference in magnitudes is 5, we take 2.512 to the fifth power, and we get 100, which means that star A is 100 times brighter than star B. So if you have, for example, 100 star Bs with a apparent magnitude of 4, they would give out the same amount of light as a single star A with a apparent magnitude of -1. So now you can say, well, how much brighter star B compared to star C? Well, if you take a look at the difference in the magnitudes, the delta M here would be equal to 9 minus 4, which is 5. So since the difference in magnitudes is 5, you can say then that star B is therefore 100 times brighter than star C. Now, how much brighter is star A compared to star C? Well, the difference in magnitudes is 10. So what we do there is we take 2.512 raised to the 10th power, and that gives us 10,000. Another way of looking at it is it's twice 5 magnitudes, so it would be 100 times 100, which is 10,000. So star A is 10,000 times brighter than star C because they differ in apparent magnitude of 10. So the way we can then figure this out is if you just have a series of delta M's and you want to know the ratio of apparent brightness. If the difference is 1 magnitude, well, that would be 2.512 to the first power, which is about 2.5 times. So you can say that if the difference in magnitude is 1 magnitude, then one star is 2.5 times brighter than the other. If it's 2 magnitudes, 2.512 raised to the second power is about 6.5. 2.512 to the third power is about 16. 2.512 to the fourth power is about 40. And 2.512 to the fifth power is 100. So there you can see that if the difference in magnitude is 1, 2, 3, 4, or 5, you can see that one star is that much brighter or dimmer, if it's a dimmer star, in those terms. Now, difference is 10. We get 2.512 to the 10th power, which is about 10,000. And then 15 would be 2.512 to the 15th power, which is 100 times 10,000, or 1 million. And you can see that for every additional 5 magnitudes, you simply add 2 more zeros to it. So 2.512 to the 20th power is 100 million. There's a comma there. And 2.512 to the 25th power would be 10 billion times. There we go, a 1 with 10 zeros behind it. So that's how we determine the difference in brightness, apparent brightness again, between two objects. Simply find out what the apparent magnitude is, find the difference between the two, and then just take the number 2.512 raised to that difference, and you get the difference in apparent brightness. And that's what we mean with the magnitude scale. So it makes a lot of sense to use a magnitude scale, because if you started using these really big numbers, it would get kind of messy. It's a lot easier simply to say, oh, we have a star of magnitude 5 or an object magnitude 15. And quickly, for an astronomer, we get a feel of how bright or how dim that is. Matter of fact, Pluto, for example, which is that body out there that used to be a planet, now is considered what we call a trans-Neptunian object or a Kuiper belt object, has a magnitude of about 15. And that's why it was so difficult to detect it, because at magnitude 15, you need a pretty good sized telescope in order to be able to see something that dim. And again, that's how we use our magnitude scale, in this case what we call the apparent magnitude scale, in order to avoid using those big numbers. And hopefully that gives you a pretty good idea of what an apparent magnitude is and the apparent magnitude scale. Welcome to lectureonline, and to give us some idea of what apparent magnitude really means is let's have some examples here. So I put down a list of examples. Again, reviewing that the apparent magnitude scale is a numeric scale. It goes all the way from some negative values to positive values. Negative values or smaller values are brighter larger values are dimmer. So it's brighter on this side of the scale, and it's dimmer on this side of the scale. And the dimmest object that we can see with the naked eye without any aid of binoculars or telescope, anything like that, is +6 magnitude. Anything beyond that, you can no longer see it with the naked eye. You need some larger aperture. Also, to compare the brightness of things, the way we figure that out is, let's say you want to compare a star that has magnitude +1 to a star that has, let's say, magnitude +4. Let's call this star A. Let's call this star B. What you need to do is find the difference in the magnitudes, the delta M as we call it, and the difference in brightness can be defined by taking the number 2.512 and raising it to the difference in magnitudes, the delta M as we call it, because magnitudes, we use small m for that for apparent magnitude. And so this would be equal to 2.512 raised to the 4 minus 1, which is third power. Then we come up over here, and so 2.512 to the third power is about 16, which means that star A is the brighter of the two stars, and it is 16 times brighter than star B. So with other words, you would need 16 stars like star B to put out as much light as one star of type A. All right, now here's some examples. Our sun is, of course, the brightest object in the sky, not because the sun is particularly bright as a star, but because it's so close. It has a magnitude of minus 26.7, which put it way over here on the magnitude scale. The moon is the second brightest object in the sky. We can actually see the moon during the day with the sun shining. It has a magnitude, I should say apparent magnitude of minus 12.6. Venus, besides the moon, the brightest object in the sky at minus 4.4. It's the brightest planet and it's much brighter than any star out there. Jupiter is also brighter than the brightest star at minus 2.6. And finally, the brightest star is Sirius. This is a star in the constellation Canis Major. It is a minus 1.4 apparent magnitude. So how much brighter is Venus compared to Sirius? Well, notice the difference. If you compare the two, the difference would be, the delta M would be equal to 3. And here that fits right into the example. That means that 2.512 to the third power is 16. And therefore, you could say that Venus is 16 times brighter than Sirius. It puts out, at least from the way we can observe it from here, we can see 16 times as much light coming from Venus as we can see from Sirius. And of course, Venus doesn't actually put out light itself. It simply reflects the sunlight. Betelgeuse is a big reddish-looking star in the constellation Orion. And it has an absolute, not an absolute, but an apparent magnitude of plus 0.58. So the difference between Sirius and Betelgeuse is about 2 magnitudes. So the difference, the delta M here, is about 2. And again, coming over here, 2.512 to the second power is 6.5 times. In other words, Sirius is 6.5 times as bright as Betelgeuse in the sky. In actuality, Betelgeuse is actually a brighter star, but it's so much farther away than Sirius. Sirius appears brighter to us, and it's all about, at this point, apparent brightness. In a later video, we'll show you something about absolute magnitude. Polaris is that star that always is pointed really close to the north, and it is a fairly bright star at plus 2.0, of course, not nearly as bright as Sirius, or not nearly as bright as Betelgeuse. Notice that the difference between Sirius and Polaris is about 3.4. 3.4, that puts it somewhere around maybe 25 times as brighter, so for Sirius compared to Polaris. Then we go all the way to the other side of the scale. Pluto is a very, very dim object. It's a very small body, way beyond the orbit of Neptune typically, and it has a magnitude of plus 15. Of course, that depends a lot upon where Pluto is in its orbit. Sometimes Pluto is only 30 astronomical units away from the Earth, and sometimes it's 50 astronomical units away. So you can see that the brightness of Pluto will vary tremendously depending upon where in its orbit it's at. The largest telescopes, earthbound telescopes, because of the atmosphere makes it very difficult to see very sharp images with large telescopes, but they can see objects down to a magnitude of about plus 21. Plus 21 is extremely dim. If you compare, let's say, plus 21 to Polaris, that difference is almost 20 magnitudes. So let's just say about 20 magnitudes when you come over here. 20 magnitudes, 2.512 to the 20th power, that is 100 million times. In other words, a large telescope can see objects that are 100 million times dimmer than the star Polaris. It's amazing what they can do. And then, of course, Hubble is the champion of them all. Notice it can see objects to dimness, in a way to, we call it apparent brightness, but at this point you could all talk about something really, really dim. At plus 30 magnitude, notice the difference between, like, let's say Betelgeuse and Hubble is 30 magnitudes. What would 30 magnitudes signify? So put another row in there, 30 magnitudes, that would be 2.512 to the 30th power. And that would be another 4 zeros behind that. So it would be 10 billion, that would be 1 trillion times. So that's a million, that's a billion, and that's a trillion. In other words, the Hubble Space Telescope can pick up images that are 1 trillion times dimmer than a star like Betelgeuse. It's absolutely amazing what we can actually see with Hubble, and the reason, of course, it's up in space. There's no atmospheric interruption, no atmospheric blurring of any type, so you can see very, very dim images to a dimness, I guess it's still apparent magnitude of plus 30. So hopefully that gives you a good feel of what apparent magnitude is. Again, it's the magnitude or the brightness that the object appears to us from here on the Earth. It doesn't reveal anything from its true brightness, because it could be a very dim object that's really close, appearing bright, or a very bright object very far away, appearing dim. It's just the way it appears to us from the Earth. How bright does it appear? That's what we call apparent magnitude, with some good examples. Welcome to Lecture Online, and now we're going to look at what we call absolute magnitude. In the previous videos, we looked at apparent magnitude, how bright things appear in the sky relative from where we are looking. So relative from the Earth, we'll look at the object in the sky, stars, galaxies, nebulas, whatever they may be, and they appear to us at a certain brightness, so that's called the apparent brightness. But the absolute brightness is how bright they actually are. Now, that's kind of a strange concept. How bright are they? Well, what we can do is we can put the object at a standard distance away from us. If we put all the object at that distance, then we would compare the brightness to one another. Matter of fact, the absolute brightness of an object is equal to the apparent brightness of the object if it's placed at that standard distance. The question is, what is that standard distance? And it turns out how bright an object would be, so absolute magnitude is how bright it would appear at the standard distance of, and we picked that to be 10 parsecs. Now, of course, 10 parsecs, since each parsec is 3.26 light years, that would be the same as 32.6 light years. So, the absolute magnitude of an object, of a star, a galaxy, whatever we may be looking at, is equal to the apparent brightness if we place the object at a distance of 10 parsecs. Or 32.6 light years. Excuse me. All right, so for example, we have the star Betelgeuse, and it has an apparent magnitude equal to plus 0.58. Actually, Betelgeuse varies a little bit in brightness because it's kind of a variable star, but the average magnitude, absolute, or I should say the average apparent magnitude is plus 0.58. Now, what would happen if we took Betelgeuse and placed it at the distance of 10 parsecs away? So here's Betelgeuse, and it turns out if we placed it there, the apparent magnitude would be minus 6, which makes it the absolute magnitude. So big M is equal to minus 6.0 for Betelgeuse at a distance of 10 parsecs, and the apparent magnitude, small m, is equal to 0.58. So when we use small m, we do mean apparent magnitude. And when we use the big M, we call it the absolute magnitude. So if we place Betelgeuse at a distance of 32.6 light years, it would appear at a minus 6.0. It would be brighter than the planet Venus by actually quite a bit. It would be brighter by almost a factor of 5. So Betelgeuse would look 5 times as bright as Venus at a distance of 32.6 light years, but the way it looks to us from wherever it is, it's only a plus 0.58. So it's a lot dimmer where it is than what it would appear to be if it was 10 parsecs away. Answer is, Betelgeuse must be much farther away than 10 parsecs or 32.6 light years because it appears a lot dimmer to us at the distance where it's at than what it would be if it was at 10 parsecs away. Now, how does that compare to our sun? Well, if we took our sun and placed it at a distance of 10 parsecs, you would be surprised. It would have a magnitude, so this would be Betelgeuse, and the sun, magnitude of the sun, would be about a plus 4.8, approximately in that neighborhood. So notice how much brighter Betelgeuse is compared to the sun at the same distance. So that's how we find the absolute magnitude of a star. We simply imagine that we place it at a distance of 10 parsecs, and then we calculate how bright it would appear if it was at that distance, and that's how we can compare one star to the next. So you can see that in this case, the sun is a much dimmer star than Betelgeuse in actuality. Of course, the sun, being the closest object in the sky to us, as far as stars is concerned, is a minus 26.7 for apparent magnitude, when Betelgeuse is only a plus 0.58. But side by side, at the standard distance of 10 parsecs, Betelgeuse is much brighter than the sun, therefore it puts out a lot more light. Now, how much brighter is that? So using these numbers right here, the delta M would be equal to 4.8 minus a minus 6.0. That would be about a 10.8 difference in the magnitudes. Then what we do with that is we take 2.512 raised to the 10.8 power, and with a calculator, we'll find out really quick. 2.512 e to the 10, let me do that again. 2.512 raised to the 10.8 power. It's, about 21,000 times. So that means that Betelgeuse is 21,000 times as bright as the sun. If you could put them side by side, you would need 21,000 suns to put out as much light as Betelgeuse. So there you can see that Betelgeuse is indeed a very bright star, partially because it's a huge star. It's enormous in size and therefore puts out a lot more light. So that's what we mean by absolute magnitude. It's simply a comparison to objects placed at the standard distance of 10 parsecs. And in the case of Betelgeuse, it is an enormous star. Are the stars bigger and brighter than Betelgeuse? Yes, there are. Are the stars dimmer than the sun? There's plenty of those. So it goes all over the gamut. There's an enormous range in brightnesses, but at least you can see just with these two stars in comparison. What's interesting to note, imagine that we're looking at a star like the sun, the size of the sun, at 10 parsecs away. If the magnitude then it would appear at 4.8, you could barely see that with the naked eye. Matter of fact, living in a city environment with street lights, you wouldn't even be able to see the sun at a distance of 10 parsecs. And yet, if you were to place Betelgeuse at that distance, it would be an enormously bright object in the sky. So that gives you a new appreciation for the difference in sizes and the difference in brightnesses. So that's what we mean by absolute magnitude. Welcome to our lecture online, and now we're going to talk about how we can find the distance to stars if we know both the absolute magnitude and the apparent magnitude. Remember, the apparent magnitude is how bright the star appears to us from the Earth. The absolute magnitude is equal to what the apparent magnitude would be if we place the object, in this case the star, at the standard distance of 10 parsecs away from the Earth. So here we have an observer looking at a star. There's certain apparent magnitude. In the case of Betelgeuse, the apparent magnitude of the star, the way it looks to us from wherever it is, has a magnitude of plus 0.58, which still makes it one of the brighter stars in the sky. But if we were to place it 10 parsecs away, it would have a magnitude of minus 6.02, which makes that the absolute magnitude. Since the absolute magnitude is minus 6, that makes it a very, very bright star. Remember, our sun, if we place our sun over here, its absolute magnitude would only be a plus 4.8. So a minus 6.02 is much, much brighter than a plus 4.8. All right, so now what we're going to do is, based upon that information, we should figure out where Betelgeuse actually is, how far it actually is to Betelgeuse. So starting out, putting Betelgeuse over here, it would have an absolute magnitude equal to minus 6.02. The fact that it has a dimmer number wherever it is, so the apparent magnitude is actually a plus 0.58, that means it must be a lot farther away than 10 parsecs. If it's dimmer, if its apparent magnitude is dimmer than its absolute magnitude, it must be farther away. The question is, how much farther? Well, the way we do that is as follows. First of all, you find the difference between the magnitude. In other words, we take, in this case, the apparent magnitude minus the absolute magnitude, and in this case that would be a apparent magnitude of plus 0.58 minus a minus 6.02. So the difference in magnitude between the apparent magnitude and the absolute magnitude is actually a 6.60. That's the difference in the magnitudes. All right. So what we do with that now is we go ahead and find out what that means in luminosity. What is the difference in luminosity if the magnitude is 6.6? And there we can say that the difference in the luminosity, the difference in the intensity or luminosity, is equal to 2.512 raised to the delta m. All right? So that would be equal to 2.512 raised to the 6.6 power. If we then grab a calculator, figure that out, 2.512 raised to the 6.6 power is, see here, 4,000, wow, I need my glasses for this one. It's too dark for me to see. 436.646. 436.646. So that is how much dimmer it appears where it actually is compared to what it is or what it would be if we place it 10 parsecs away. Or you could say, if we take Betelgeuse, which must be way out here somewhere at a very far distance, if we take Betelgeuse and bring it to a distance of 10 parsecs away, its intensity or luminosity would increase by a factor of 436. It would be 436 times brighter at 10 parsecs than where it actually is. Now to find the distance is equal to 10 parsecs multiplied times the square root of the difference in the luminosity. So now we take this number right here, take the square root of that, and multiply times 10 parsecs, and that's where Betelgeuse actually is. So let's work that out. So the distance to Betelgeuse is 10 parsecs times the square root of 436.636 or 646. Not that those decimal places really make much of a difference for us. So let's take the square root of that. Okay, and let me show you what that is. So that's equal to 10 parsecs times the quantity 20.9. And so that would be equal to 209 parsecs. So that would be the distance to Betelgeuse. Converting to light years, then we have to multiply this times a ratio of 3.26 light years per 1 parsec. And so multiply times 3.26 equals, and that would put it at about 681 light years, which is right around the distance that we currently know Betelgeuse is. It's very difficult to get accurate readings on where things are, especially stars, but that is fairly accurate to the point where we know that it's right around 680 light years to Betelgeuse. So, again, the absolute magnitude is the brightness an object, in this case the star Betelgeuse, would be if we place it 10 parsecs away from the Earth. So this distance is 10 parsecs. The fact that the apparent magnitude, it's much dimmer, then we know that Betelgeuse actually is much further away from us. How do we find that distance from the Earth to Betelgeuse? Well, what we do is we take the difference in the magnitudes. The difference between minus 6.02 and plus 0.58 is 6.6. We then use that we then use it as the exponent of the number 2.512 to convert from the difference in magnitude to the difference in luminosity. Luminosity is the brightness in terms of watts per square meter. So we then raise 2.512 to the difference in magnitudes, and out comes 436. That means that Betelgeuse is 436 times brighter if it was at a distance of 10 parsecs compared to where it actually is. We then find the actual distance by taking 10 parsecs and multiplying it times the square root of the difference in luminosity, which is the number we got right here. We plug that in here, and I keep forgetting to put the end parentheses there. So the square root of 436 is about 20.9. 10 times 20.9 is 209 parsecs. Converted to light years is about 681 light years. And that's how we find the distance to any object, any star, galaxy, whatever it may be, using this particular principle. That's how we do that. Welcome to our lecture online, and now we're going to find the distance to a supernova knowing that the absolute magnitude of a type 1a supernova is about minus 19. And let's say that we're observing it and it has a magnitude, a apparent magnitude of plus 8. So it wouldn't even be visible to the naked eye, but through a telescope we see a supernova go off. We see it as a magnitude 8, and we know that when we place it at our standard distance of 10 parsecs away, 10 parsecs, which is 32.6 light years, if that same supernova would be at a distance of 10 parsecs away, it would show up at a magnitude m equals to minus 19.0. Now, how far away is that supernova? Again, the way we start is by taking the difference between the magnitude, so this is equal to m minus m, and so we start at 8.0, that's plus, minus a minus 19.0, so the difference is 27 magnitudes between the way it appears and the way it would appear if it was only 10 parsecs away. The fact that it's a whole lot dimmer the way it appears, it must be really far away. We're trying to find that distance. So the next thing we do is we convert that to the difference in the luminosity. So that would be equal to 2.512 raised to the difference in the magnitudes. So 2.512 raised to the 27 power. So let's find out how big that number is. That's probably a very big number. So 2.512 raised to the 27 power. And we get, let me try my glasses here, 6.317 times 10 to the 10th, and that would be the difference in the luminosity if we see it where it actually is compared to what it would be like if we place it 10 parsecs away. Now for the distance. The distance is going to be equal to 10 parsecs times the square root of the change in the luminosity, the difference in luminosity if compared to where it is to what it would be if it was 10 parsecs away. Now, why do I do the square root of the luminosity? Because we know that the intensity or the luminosity is proportional to 1 over the distance squared. So that's why the square root is necessary to find the distance, right? Because if you take the square root of both sides, you can see that 1 over r is proportional to the change in the luminosity. All right, now let's plug the number in. So the distance is equal to 10 parsecs times the square root of 6.317 times 10 to the 10th. So let's take the square root of that. And that distance would be equal to 10 parsecs times, and it would be 251,342. And so therefore the distance would be equal to 2,513,420 parsecs. And of course, if we then want to convert it to light years, then we have to multiply this times the ratio of 3.26 light years for 1 parsec. And so the distance in light years would be 8,193,700 and try it again. 2 million times 10. I forgot the times 10. So 8,193,750 light years. There we go. So it would be about a little over 8 million light years away. So it would be in another galaxy. Since our galaxy is not nearly that big, we can then say that we saw that supernova in some galaxy about 8 million light years away. And this is how we do that. Again, take the difference in the magnitudes between the apparent and the absolute magnitude. When you have the difference, use it as an exponent to find the difference in the luminosity at the location where it actually is, the apparent luminosity, and the luminosity what it would be, the absolute luminosity, if we place it 10 parsecs away. We get that difference in the luminosity. We take the square root of that number, multiply times 10 parsec. That gives us the distance in parsec. If you wanted light years, multiply times 3.26 to get the distance in light years. And that's how we find the distances, knowing both the absolute and the apparent magnitude. So the key then always is, well, apparent magnitude is easy to measure. We just take a telescope, we measure it, you use a correct light sensing mechanization to find out what the magnitude is, the way it appears. And then we have to find a way to determine the absolute magnitude. Once we know both, we can calculate the distance. And that's how we do that. Welcome to Electron Line, and now we're going to look at what we call the angle of parallax. One of the ways that we were able to figure the distance to stars, before we had really any other method, was called the angle of parallax. It turns out that when we observe a star from the Earth, when the Earth is in this position in its orbit relative to the Sun and the star, we can draw a line directly from the Earth to the star and find its location relative to stars that are really, really far away from it. So here, let's say that these are the stars that are really far away and basically do not change position anytime during the year because the movement of the Earth is insignificant compared to the enormous distances of those stars. Then that star would show up against the background of stars in a particular location. So the star would be over there at that point in the Earth's orbit. But 3 months later, when the Earth is over here, and then you look at the star, you can see that this star would now appear at a different location relative to the background stars. And this angle, which is this angle right here, it's called the angle of parallax, which is the same as this angle right there, can be measured by seeing where that star appears at different times in the Earth's orbit. The larger that angle, the closer the star. The smaller the angle, the farther away. For example, if we take a look at this faraway star right there, you can see that the relative positioning of where it would appear at this point in the Earth's orbit, and then where it would appear at some other point in the Earth's orbit, you can see that that angle would be a lot smaller, and so therefore you realize then that the object is a lot farther away. I didn't quite draw that correctly, did I? So let me try that again. So it's actually like this. So it would only be a minuscule movement in the star's position relative to the faraway stars, and so therefore we would know that the star is much farther away. The equation to actually figure out the distance is right here. The distance in parsecs to that star that we are trying to find the angle of parallax of is equal to 1 divided by the angle measured in arc seconds. In other words, if the angle that we measure is 1 arc second, then the distance to the star would be 1 parsec, which is 3.26 light years. Now, as an example, what if theta was equal to a half arc second? Then you know that the distance is equal to 1 divided by 1/2, which is equal to 2, and of course the units would be 2 parsecs. So it would be 1 parsec divided by 1/2, which is 2 parsecs. What if the angle was 1/3 of an arc second? If the angle measure was equal to 1/3 of an arc second, then the distance would be 1 parsec divided by 1/3, which is equal to 3 parsecs, and so forth. So whatever the fraction is, we take the inverse of that, and that would be the distance in parsecs. Now, back in the old days when we had, the ability only to read the angle of parallax, to maybe the best we could do would be about 1/5 of an arc second, which means that we were able to find the distance of stars out to about 5 parsecs, which was about 15, 16 light years, and that was the best we could do. So we could actually find the distance to about the 100 nearest stars using this particular technique, because there's about 100 stars within about 15, 16 light years from the Earth or from our Sun. So that was actually a pretty good method to find the distance to those stars. And then once we found the distance of those stars and we applied our knowledge about what those stars looked like, what color they were, what temperature they were, we were able to find out some amazing things. And we'll show you in a later video what we actually did with that. But here is sufficient to see that using the angle of parallax, we're able to find the distance to those stars. It's kind of the way our eyes work. Our eyes, the reason why we have two eyes is because we can look at the same thing from two different directions. Our brain will take that angle, and from that angle we actually get depth perception. So if we didn't have two eyes, it would be very difficult for us to have depth perception. Matter of fact, try it, cover up one of the eyes, look around you, and all of a sudden you realize it's pretty difficult to figure out how far things are. With two eyes open, it is much easier. And so this is kind of like a two-eyed situation where we look at the same thing from two different directions, even though it's 3 months apart. And we can then, of course, see what the angle is, and from that we can figure out the distance. In order to improve our ability, what we sometimes do is we try to look at the same object from this position 6 months earlier, and then we take the angular measurement to the object, and then you can see that we can measure a much bigger angle. So what we then do is we take the angle of parallax, we take this angle and divide it by 2. We can then say, if we call this angle phi, we can then say that theta is simply phi divided by 2, just to get a better reading on it, because those angles are so hard to measure. We try to get as much of a distance over here as possible. Notice that this distance from the sun to the earth here is 1 astronomical unit. If we take the total distance across the whole orbit, the diameter of the orbit, it would be 2 astronomical units, and so you get a better reading on that. It's of course more difficult to do because here you would be looking at the object at sunrise or sunset, or right after sunset, or just before sunrise, and the same over here to be able to get that larger angle. It's a lot easier to measure it when the difference is like that. And that's the method we use for the angle of parallax. Welcome to iLecture and in this video we're going to take a look at the stellar motion. Now stars relative to us are all in motion. It may not look like that because we look at the stars every night and they appear to be pretty well in the same place relative to each other and relative to us. But yes, most stars do move, and in a lot of cases they move differently than the way we do in our own galaxy. And so what happens is, let's say we're observing a star. The star could be moving away from us or moving towards us. It could be moving to the right, to the left. Most of the time it's a combination of the two. Like in this example, maybe the motion of the star is like this, which means that it has a component of the velocity that's radially either away or towards us, and also there's a component of the velocity which is directly perpendicular to that radial arm. So we call this the radial velocity, we call this the tangential velocity. That's why we use v sub r and v sub t for radial and tangential. Now what we need to do is we need to be able to figure out what each of those two velocities is. Once we do, the velocity of the star can be found using Pythagorean theorem is equal to the square root of the vertical component squared plus the horizontal component squared, the radial component and the tangential component. So how do we find those two components? Well, the first component, the radial component, can be found by the shift in the wavelengths of the emission spectrum. For example, hydrogen has an alpha line at 656.3 nanometers. That line is created when an electron jumps from the second to the third level and then back from the third level back down to the second energy level, emitting a photon of this particular frequency. But if the star is moving either away from us or towards us, that frequency will have shifted. For example, in this case, the wavelength may be as high as 658.5 nanometers, indicating that it shifted towards the red. It is red shifted, therefore the star is moving away from us. How fast? Here's the equation. The radial velocity is equal to the speed of light times the ratio of how much that wavelength has shifted divided by the original wavelength. So in this case, that would be equal to 300,000 kilometers per second. That is the speed of light, times the difference in the wavelength from 656.3 to 658.5. That's a difference of 2.2 nanometers. And we divide that by the original, what it would be if it was not moving, which is 656.3 nanometers. And that will give us the velocity of that star in a radial direction. So 300,000 times 2.2 divided by 656.3, and we get 1005.6 kilometers per second. So 1005.6 kilometers per second. So we know that star is moving away from us at slightly over 1,000 kilometers per second. Now let's say that we observe the star and we measure where the position is, and then a year later we measure it again and we notice that it shifted to the right 12 arc seconds during that year. The way we can then find the tangential velocity is to come over here and, okay, this should be tangential, not radial. It is equal to the constant 4.74, and that constant is what we need to be able to use the units the way we do, times the angular distance traveled in a year. In this case, 12 arc seconds in a year, so we multiply that times 12 arc seconds, and then the distance in parsec, and in this case, let's say that the star was 4.5 parsecs away, so we'll put that over there, 4.5, and the answer will come to us in kilometers per second. So let's go ahead and calculate that. 4.74 times 12 times 4.5, and we find that the tangential velocity is 256.0 kilometers per second. So that would be the velocity in this direction. Here would be the velocity in that direction. So now to find the total velocity, the velocity of the star, we note that that will be equal to the square root of the radial velocity plus the tangential velocity squared, so that would be equal to the square root of 1005.6 kilometers per second quantity squared plus 256.0 kilometers per second, and we also square that. And so finally, if we square that plus 1005.6 squared equals, take the square root, and we find that the total velocity of that star is 1037.7 kilometers per second. That will be V of the star, and that's how we find it. So, any velocity of any object in space, there's a component that is directly in line, or line of sight, which is called the radial velocity, and then there'll be a component perpendicular to that. It could be like this or like that. It's always perpendicular to us. We can measure that angle, and then we combine the two velocities vectorially like this using Pythagorean theorem, and that's how we find the velocity of any object in the universe.